Good afternoon. Thank you for joining us today. Firstly, I'll tell you a little bit about myself. So I'm the Business Development Manager here at Datum Electronics. I've been involved in the marine industry for many years and been with Datum for 15 years. Previously, I've worked within Datum in the engineering department for 12 of those years. I've got an extensive knowledge of testing, integrating and installing marine shaft power meters on board vessels. And I've been involved with both commercial and military projects. And now I'd like to introduce you to my colleague, Konstantinos.
Right, I am Konstantinos and I'm the lead marine engineer here at Datum Electronics. I began my research career by working in offshore platforms back in the shipyard of King Raffles in Yantai, where we performed an energy management project. Working in the University of Strathclyde MSRC Center, we focused primarily on internal combustion engines, energy analysis, and developed a systematic methodology for ship propulsion engines energy management. Thus far, my research has been in internal combustion engines, and we're looking currently into modeling and diagnostic techniques using both first principles as well as data-driven methods. Right. So we're here to talk about condition-based maintenance. And we first begin by talking about the approach to savings. Well, certainly there are many approaches to savings in the marine industry. And a very basic one, a very big one, is implementing condition-based maintenance. This simply implies that a piece of equipment or machinery, namely, let's say, the main engine, is being closely monitored and analyzed, and the data analyzed, such that when the onset of failure or excessive degradation takes place, this is identified, and therefore action is taken in a timely manner. Consequently, this has a number of benefits. This approach has a number of benefits. Firstly, reduction in downtime from costly failures. Secondly, optimized maintenance intervals, because each vessel may have a different operating profile. Then a generic maintenance plan might not fit all. Therefore, this allows for the maintenance interval to be optimized on each specific vessel according to what it's been through. And last, it results to efficient and compliant engines, especially with the recent push in the green regulatory frameworks of both the IMO, the UK, as well as the European Union. It's something that concerns all of us. So certainly condition-based maintenance can successfully address these three things. But where does it exactly begin? Condition-based maintenance begins from monitoring the equipment. And the selection of which engine parameter one monitors is very essential, because this has to be a cheap measurement, cannot be too expensive. It has to be accurate and also reveal information about the engine. And it also has to be easy to set up and deploy the sensor, the respective sensor networks. And perhaps most importantly, it has to be able to be continuously monitored. In our experience, methods such as oil sampling and in-cylinder pressure diagrams is something that is definitely of huge value. However, one of the drawbacks there is that it cannot happen continuously. So it may be once every 3 months, once every 4 months, maybe even later. So the onset of failure of something critical may be missed in that interval, which there is no information about our system. So pretty much this leads us into a process of condition-based maintenance, where it includes of 3 basic steps, given that we have, of course, obtained the data that we are looking for. First, we analyze. Second, we identify. And third, we translate all that into action, which is to maintain accordingly. To analyze, we first gather all the data, we establish baselines, we establish trends, we filter the data in case of any outliers or any obvious mistakes or errors from the sensors exist, such as noise or things like that. That's the analyzing part. And then we proceed into, it could be arguably more advanced techniques, and one could make it as advanced as, you know, it's required, where we can do modeling, modeling of the internal combustion engine or of its specific components. We can do data-driven models, such that when we get the data that has been filtered and place it into a model that tells us more information about our system. And this process of, this sophisticated process of modeling essentially identifies the engine condition and it spots signs of faults and degradation. So this is where the data actually turns into useful information. And having that information in hand, where it tells us, for example, that, you know, we've got an underperforming turbocharger compressor, then this can be translated into action, where we can say, you know, that the filter has been clogged, or so on and so forth. And this is the last step of actually maintaining. So to give you a brief, you know, case study of how this could possibly work, let's say that we obtain the in-cylinder pressure diagram at some point in time during the vessel's lifetime. Firstly, we have to analyze the diagram. We cannot take it as is and be able to obtain something useful. What we mean by that is that we firstly have to smooth the diagram, because usually in-cylinder pressure diagrams tend to have a lot of noise inherited from the sensors. So after that smoothing happens, it has to be calibrated, which also happens through a theoretical procedure where the datum is established from where the 0 point of the in-cylinder pressure diagram is. After this is done, we can also obtain for reference the pressure at the shop tests, the in-cylinder pressure during the engine's shop tests, where we know the engine there is brand new and we have a useful reference to compare. So there's the first part. Second, we can move on to the identification part. So as you can see here, we've got with the red curve, the pressure diagram that has been obtained as a baseline, and with the black curve, the currently measured pressure curve. With these, we can do some modeling techniques, in this case, very simple ones, using an isentropic relationship to establish what the compression looks like, which is here what we see in the dashed lines, in the red and black respectively. So what that tells us is it gives us a little bit more insight. So we see here right away, without those lines, we can see that there is less of a maximum pressure. So is this only occurring during combustion, or is this also an effect of compression? This is something important to determine, because it could be the difference between a faulty fuel injector and excessive blow-by in the engine, or less scavenger receiver pressure. So certainly being able to see through modeling that dashed line gives us an image of what is actually going on, which in this case, as we can see, because the compression of the engine is also reduced, it probably means that there is something going on downstream or within the cylinder that has to do with not keeping enough compression. So this can move on after we have this part, and we've sort of established, after having analyzed the data, we sort of established some basic modeling. We can then combine also other measurements as well. Since we've established that the compression of the cylinder is suffering, it could be, say, for example, the turbocharger is not generating enough compression. In which case, to confirm that, we'd have to also obtain the scavenger pressure, which again, once we compare according to a baseline or with typical values that we're aware of, we can see if that's too little or if that is where it should be, which could indicate if it's not where it should be, some sort of fouling or maybe some sort of other fault. Conversely, if we have the exhaust gas temperatures right after the cylinder, we could see whether we've got a leaking exhaust gas valve. Regardless, the lesson here is that we need more than one measurement in order to diagnose a fault. And after that, after we've combined all of our measurements, we've we set up the framework that we need to make the diagnosis, we're able to conclusively say what the fault is. If it's a combination of signs from the measurements that point out to the turbocharger, for example, we could go right ahead and see there what's wrong, whether it's a clogged filter, whether it's a foul Del cooler, or whether it could be something else. So essentially, we learned three things from this. The first thing is that we need more than one measurement in order to make a diagnosis. The second is that we need to be able to obtain a baseline in order to compare, because that's extremely useful. And the third one is, of course, that the in-cylinder pressure is the heart of the engine, and any subsequent degradation or faults within the cylinder can certainly be visible there. So having these things in mind, what is a signal that we can obtain where it can tell us just as much as the in-cylinder pressure can? So in our experience here in Datum, that would be the instantaneous crankshaft torque. Now you can see, for example, that diagram on the right-hand side. That would be a 10-cylinder two-stroke diesel engine, where you could see how the torque fluctuates within one engine revolution. So that essentially translates whatever is happening within each cylinder to the torque that is being delivered at the point of measurement, which is right after the flywheel of the engine. So this is an extremely low cost to data size ratio. So that is certainly helpful in terms of obtaining that measurement. It's highly accurate due to strain gauging technology. Only one sensor is required to capture information regarding all the engine cylinders. And something that's extremely important, it can also be continuously monitored. And however, it does require analysis to extract and have an in-depth insight regarding what is happening within the engines, which we'll explain in subsequent slides. And now I'll pass you over to Mark, who will explain more about the instantaneous crankshaft torque.
Thanks, Kostas. So just to explain a bit more of how we do this, at Datum we already supply a very successful marine shaft power meter. The standard system works at 10 samples a second. So what we're doing is increasing the sample rate using technologies that we've learned from other industries, and we begin to sample at 2,000 samples a second. So the system we already have is very unique in the fact that it's fully modular and the only fully modular system on the market. And I'd just like to show you a short video explaining more about how our shaft power meter works. So our shaft power meter was actually designed and developed on diesel generators. So in the harshest environments, high temperatures and high RPMs. In the photo you can see here, the shaft power meter is situated between the flywheel and the crankcase sill. And another advantage of our system is that it can be fitted into very, very small spaces. So we can actually build the electronics all into the rotor band itself. So it fits into spaces as small as 100 millimeters. So we're in a joint partnership with Strathclyde University and Innovate UK called the Datum project. And this is where we're bringing the best modelling experts in the world with the help of Innovate UK to the Datum Electronics team to produce what we are now seeing as the future of condition-based monitoring.
Right. So essentially then the question is, since we have high quality instantaneous crankshaft torque data, how do we use this to obtain useful information about the engine? So the first step to that is constructing a crankshaft dynamics model. So as we can see here, as an example, there is a 10-cylinder engine, and each mass on the crankshaft of that engine is connected to the adjacent mass with a simulated spring and damper, which pretty much implies what is happening in reality, which is the crankshaft is a flexible shaft, where as it rotates, the torque that's being input on every cylinder is not transmitted exactly in the same format at the output on the flywheel. So this creates a fairly complex model where using it, we can predict based on a given input what the torque will be that we should be measuring at the crankshaft on the right next to the flywheel where the torque meter would be installed. So this would imply that we make that we build a direct model. We're using the crankshaft dynamics model and using some basic information about the engine, as well as the in-cylinder pressure diagram. We are able to predict what the torque that the engine will be producing will be. Certainly, the first benefit of that will be that we can use this as a baseline. So using the in-cylinder pressure, let's say during the ship trials or engine shop tests or at any other point in the engine's lifetime, we can predict what the torque will be that's going to be produced by the engine instantaneously, and we can compare it to the one that's being currently measured. So we can see how far or how close to that we are. So that would be the first tool. Secondly, we can do what's called failure mapping. So since there are, we can see right here, since they are the effect of certain failures, such as clogging of injectors or change in timing or loss in compression, is quite well known, its impact on the in-cylinder pressure, then these can be virtually simulated, as we've done here in this case, and their impact on the instantaneous crankshaft torque can be mapped. So by being able to, let's say, build a database, we are able to map all possible failures that we would like to consider in any combination for any cylinder or any number of cylinders and see what their impact is on the crankshaft torque. Therefore, we can compare the predicted crankshaft torque from the direct model, given these initial conditions of failure, with what is currently being measured, which is again a tool that allows us to see what is the condition of the engine. So that'll be failure mapping. As we can see here, as the in-cylinder pressure diagram is changing, so does the instantaneous crankshaft torque. Sometimes not so much, but other times more notably, depending on what cylinder, what combination of cylinders, and these factors are what contribute to this torque. Right. So over to Mark now to explain more about the instantaneous crankshaft torque in regards to our experience with V12 engines.
Kostas. So I'm just going to give you a short example of some real-time data that we've taken. Basically, as Kostas says, it's for a V12 engine. And from the engine manufacturer, we of course know the firing sequence. And when we take into account top dead center from the flywheel, we can then combine that with the perfect profile for a V12 engine. So this would be the perfect profile for a V12 over 2 rotations to 720 degrees. And each of the peaks represents one of the cylinders. And as I say, if we take TDC into account, we can then identify each of these individual cylinders and monitor for changes. So on the next slide, you'll see some real torque data. And this was actually taken from a cruise ship, one of the diesel generators on a cruise ship. And this is the actual torque signature for that particular engine. We did many months of study on board numerous vessels, looking at different diesel generators and main engines. And in the next slide, we will be able to show you before and after an event. So on the left is the healthy torque profile, and the right is a profile from 2 weeks later. And what actually happened, and if costs you can point out to the individual cylinders themselves, was a gasket failure. So the whole idea of our condition-based monitoring system is that it's also a predictive system. So the intention is that through the intelligent modules and AI that we use within the system, we never get to that profile on the right. We maintain the healthy profile, which is on the left.
So essentially, to summarize, a direct crankshaft dynamics model can be used to establish a baseline as well as a database of possible failed conditions, which we can always go back and compare against, given our current measurements. Virtual faults can be therefore introduced in any cylinder, and the response in the instantaneous crankshaft torque can be mapped and stored. So pretty much that explains the direct model. However, we're making progress on what we call the inverse model, which essentially works backwards in much greater detail than what the direct model would do. So we now have the torque that's being measured, as we can see here in this example, where we have, again, a 10-cylinder 2-stroke engine with this specific torque profile. It is being fed into an inverse crankshaft dynamics model, and it is identified that we have a misfire at cylinder 7 and 1, which is not, as you can see from this profile, is not exactly obvious to see. So what is happening there is actually we're managing, by using a self-adaptive algorithm, we're managing to work backwards and see what cylinders are responsible for the specific change in the torque that has occurred. Obviously, as the model grows and as the data becomes more and more, we're able to make this more robust and actually identify specific changes within the in-cylinder pressure, such as a small change in timing, or drop in the maximum pressure, or drop in compression. So pretty much this places us, our goal is that of continual improvement. Certainly the crankshaft dynamic, the inverse crankshaft and the direct crankshaft dynamic models work. However, what our goal is to improve the self-adaptive algorithm robustness so that we can identify in detail what is happening within each cylinder, and therefore effectively be able to have an on-demand in-cylinder pressure diagram or something equivalent that we'd have access to using our continuous monitoring system. And then we could be able, then by connecting into the engine's CAN bus or into any existing network, sensor networks on the ship, we would be able to combine this with a thermodynamics model, which is currently also under development. Therefore, we'll be able to perform component-wise degradation analysis by looking, for example, at temperatures before and after the turbocharger's turbine, or after the compressor, or after the air cooler. We'd be able to work on a component by component basis using that thermodynamics model, which we would be able to compare our measurements against. Also, the end idea would be that we could couple the crankshaft dynamics model with the thermodynamics model to give us a holistic perspective of what is happening within the entire engine system. And last, what is also in the pipework is frequency analysis of the instantaneous crankshaft torque signal, which in our experience in regards to this matter can provide us information in regards to effects that affect the friction of the engine, such as a failed bearing or piston scuffing. So you get extra frequencies in the instantaneous crankshaft torque signal that you can't see easily by the naked eye, where such an analysis will be able to identify those.
We've got a website for our Datum product, which we'll be launching actually on the 3rd of June. And that's available to view at www.datumhawk.com. On there, you'll find lots of information about the product and all the benefits of the product itself. And we're actually hosting another launch webinar, again on the 3rd of June at 3 o'clock British time. And you can access that by going to www.datumhawk.com/launch. So we actually have some questions come in via Slido, and we're quite happy to take as many questions as you'd like to send through. I'll just ask you the first ones here, Costa.
Yeah.
Okay. Are there limits to the data output types that can be used if using high sample rates?
I think, Mark, regarding the sensor, you have more, you can give a more accurate response than I on this one.
Okay, so we've done a lot of study into the sampling and the high samples. For things like gearbox meshing in the automotive industry, we go to speeds up to 20,000 samples a second. What we've realized from the extensive testing we've done in the past years in the marine industry, there's not a lot to be seen above 2 kilohertz frequency in the main shaft line itself. So currently the system will monitor at 2,000 samples a second. Next question, for you, Kostas. Have you considered fault scenarios such as hull and prop fouling, heavy weather, etc.?
Yes, this is not something that can be identified from the instantaneous crankshaft torque. Well, it can, but there are better ways to do it using the traditional steady state approach. Actually, we've made a publication in Strathclyde regarding that, where we took data, which the sample rate was fairly slow. It was once per 4 hours, I believe. And we analyzed those such that we can find the baseline again from the shop trials and compare it to how the propeller curve would change over time, given that there's more fouling, or if there are any sort of spontaneous events such as heavy weather, where they'd increase spontaneously the propeller curve and then bring it back down again. So that wouldn't be as a consistent increase as the fouling. But certainly, yes, this can be done with steady state data. It can be done, and it has been done, and we have experience with this specific part.
Absolutely. So just to add to that, so the standard system, and when we sample at the slower rates, 10 samples a second on an intermediate shaft, we can certainly see from having torque and thrust gauges any drag or changes in propeller condition from the shaft power meter system. The dynamic sampling that we use obviously looks at the engine condition. At the same time, we're able to assess the condition and give a baseline for the propeller and the hull using the slower data, as Kostas says, using the traditional methods. So it's a great system that you can do both at once. So to the next question, what's the minimum shaft diameter for installation? Currently the system goes down to 140 millimeters as standard. We can go to smaller sizes than that, but the majority that we do are nearer the 400 millimeter size. We've actually done the world's largest torque transducer. It wasn't actually for the marine industry, it's for the wind turbine sector. But these have shafts of around 1.2 meters diameter. So the nice thing with our fully modular system is that we can fit on to the majority of sizes of shaft. but we do have other products that we can use on smaller shafts also. And to the next question. This is a good one for Kostas. How does the system compare with the inbuilt electronic two-stroke engine designer's diagnostic solutions?
The difference with this is that we are taking a signal that not many people have access to, which is the instantaneous crankshaft torque. And what we can do there is that we can use all these techniques in order to identify in real time what is happening within each cylinder. So that's what the power of this signal is, of the instantaneous crankshaft torque. So we can work backwards and we can see within each cylinder real time what's happening without having to deploy massive networks of sensors. Obviously, as we said, there is quite a lot of work to be done additionally in order to make those predictions very robust. But certainly that is the idea, which is, to the best of our knowledge, not something that anybody else uses in order to accomplish those diagnostics in such a way that is non-intrusive as well to the engine.
Okay, and to the next question. Are these AI solutions are based on stochastic modeling or deterministic based on real data?
Sorry, I did not get that. Can we ask that again?
Are these AI solutions based on stochastic modeling or deterministic based on real data?
Yeah, thus far, it's primarily at this point is deterministic, which is, you know, there is some sort of filtering and, you know, processing to the data. However, the model is being deterministic. As this expands, because especially the inverse model, because it's a self-adaptive algorithm, we will have to introduce, especially due to the volume of the data that we're looking at obtaining, stochastic techniques such as data-driven modeling. So certainly this is something that we've started incorporating now, but we'll primarily give emphasis to that in the future once our database is greatly expanded. So once we're looking about, you know, terabytes upon terabytes. And this is going to be when we're going to have the infrastructure to actually deploy these successfully.
Thanks, Kostas. And next one is, how does the system recognize if the torque is reduced on the shaft due to engine bearing damage or shaft bearing damage?
Yeah, that's a good question, actually. That is where the frequency analysis comes in. Usually there are very distinct features when there is some sort of a change in the frictional effects within the engine, be that bearings or piston rings or whatever. So right away, when there is a bearing that is starting to go, certainly there's going to be a change in torque. But in order to correspond this into an effect that has to do with friction, performing frequency analysis on top of that would be something that will tell us that.
Okay, cheers, Kostas. And another one. For condition monitoring of a four-stroke to be acceptable for class, we would also need to see what's going on in the bearing. Any thoughts?
Yeah, certainly this is in the works of implementing by doing frequency analysis in order to see what is actually happening in terms of the frictional effects that are taking place within the engine. So yeah, certainly this is a consideration that we're having.
Thank you. And the next one is, how often does the model need to be updated with more data in order to be even more robust and even more accurate?
That actually depends. In its current format, it doesn't need to be, it has a specific set of training data that doesn't need to change. However, as I see this evolving, it will be using data that has been already obtained, partition it into an 80-20, 70-30, and use some of it as training and some of it as real data, as the real test data on the go continuously. So that will be the procedure.
Thank you. And the next question, how does the one-time calibration work? Does the system compensate for electronic drift over time? I'll give you a break here, Kostas, I'll take that one. So the nice thing with our system is that directly from the strain gauge, we digitize the signal before it goes to the amplifier. So unlike many other systems in the market where they have analog circuitry at the front end, everything we do from the strain gauge onwards is digitized, which means it's not susceptible for changes in temperature in the engine room. So we did not suffer with drift with our systems. So the day it's installed, it's calibrated, it's zeroed, and that's it for the life of the system. The calibration itself is theoretical, and as long as no changes in the shaft itself, as in physical changes, we use certain constants based on the gauge factor, the Poisson's ratio, Young's modulus, and then of course the shaft diameter. So unless the physical shaft changed itself, there is no need to recalibrate. So as I say, the day it's installed, we zero, we calibrate it, and that's there for the life of the system, which is normally for the life of the vessel and beyond. I should also add that when I say about the life of the vessel and beyond, the system itself is the only recyclable system on the market. Due to our unique fully modular design, it means that if you were to sell an old vessel or purchase a new vessel and want to transfer the shaft power meter from one to another, even if they've got completely different diameter shafts, you can do that with our system by adding and removing links. So as I say, it's again on the green front, it's actually the only recyclable system on the market. And the next one is due to different sleeves need to be installed to get torque and thrust measurement, are 2 strain gauges needed if I only want torque measurement. If we're measuring torque and thrust, yes, we use 2 gauges, one at 45 degrees. For torque measurement, you can use 1 strain gauge. We always put 2 down. So there's 1 there for redundancy, should there be any issues with the main sensor itself. But yes, it's 1 per channel, so you can have 1 for torque and 1 for thrust. Okay, I think that's to the end of our questions.
Yeah, thank you very much, everyone. That concludes the presentation. Thank you for being here with us.